Chapter 13, Sampling Distributions. Suppose the x is the random variable, could be discrete, could be continuous, and say this is the probability density function for that random variable. And suppose mu is the mean, and the sigma is the standard deviation, and the sigma square is the variance. And in general, these are population parameters we do not know, so we want to estimate them, either these parameters or functions of these parameters. Sometimes you might be interested in like a mu divided by sigma or something like that. Okay, so we are going to estimate these things using a random sample. So you pull a random sample, x1, x2, xn, say this is the random sample. Sometimes there are other ways to pull random samples, but we are dealing with a simple random samples. Okay, so we using this random sample, we are going to calculate a quantity, a function of your random sample, so which is known as a statistic. So could be, say for example, you pull a random sample, you are calculating the average. So that is a statistics. So sometimes maybe like we decide to throw you remember the trim mean, you throw out the highest 5% as well as the lowest 5%. So your statistics could be that. Or if you are interested in the sigma square, so your statistics, your estimate could be, you already know that estimate could be sample variance. Okay, so or the standard deviation. So like that. So when you pull a random sample, you're not going to get the same values again and again. So maybe this one, if you pull first time around, you might get one value, second time around you get another value, and so on. So these values, if you look at the probability, pretty much this is going to be, in other words, you are going to get different values. So this is itself a random variable, these quantities. So the probability distribution of these quantities, they are known as sampling distributions. So in other words, when we say sampling distribution, is a sampling distribution. We are looking at x bar. So x bar has a sampling distribution of x bar, or the sampling distribution of x square, or the sampling distribution of s. So first we are going to study the sampling distribution of x bar. So and then later we will look into the other things. So sampling distribution of x bar, say for so I'm going to give you three theorems. So the first theorem, so say x, the initial population, x has a normal distribution with mean mu and the variance sigma square, this nice symmetric curve. So you pull a random sample and you look at the average. So the average, the theorem says that the average always will follow another normal curve. The mean is going to be the same as the original mean, but the variance is going to be the original variance divided by n. Or if you're looking at in terms of the standard deviation, the square root of that, which is the sigma over square root of n. So in other words, so if you're looking at the x bar curve, x bar is going to be centered around the same mu value, but the variance is going to be the original variance divided by n. Since you're going to divide by a bigger value, so the variance is going to be less. So it's kind of centered around, getting closer and closer to the mu, basically. Okay, variability is less compared to the original curve. Okay, so in different words, basically the mean of x bar, so I'm talking about the mean of x bar, is same as the original mean. The variance of x bar is going to be the original variance divided by n. Standard deviation of x bar is going to be the square root of that, which is the sigma over square root of n. So it's always follow normal curve. Okay. So the second theorem is that if here now I have any other curve rather than the normal curve. So if you pull a random sample out of that, so the mean and the variance, okay, they're going to stay exactly the same as in this case. So the mean is going to be the same mean and the variance is going to be the same variance, those two. But so we did not say that the probability distribution. Here there's another piece into that. So this is going to follow a normal curve. So here this curve could be a little bit somewhat something like that. Okay, so it's depend on that. So depend on the n. So the third part of this theorem is the important part. If you, for large n, if you pull a large sample, then the x bar is going to be, bar is going to follow a normal curve. That's what it's going to say. So not only that, the mean and that, this is correct from this theorem. Not only those two, so not only those two, the curve is going to follow a normal curve. See, you can see that this is a very powerful theorem because you already know how to calculate probabilities using your tables. So you can use those tables to figure out probabilities because this is a nice curve. Okay, so let me write down this theorem in a formal way. So central limit theorem goes like this. So if you, from any distribution, say these are the mean and the variances, if you pull a random sample, so the only two conditions, the mean got to be finite and the standard deviation got to be finite. In other words, they need to have values. You cannot. So in this class, all the things we look at, they have finite mean and the variance in general. Okay, so for large n, the distribution of x bar is approximately normal with mean mu and the variance that, or the standard deviation square root of that. Not only that, for large n, this is normal. Okay, so you can use, if you are dealing with a large n, you can use the normal tables to figure out probabilities. So the note 1, larger than, better the approximation. So basically, the second note, rule of thumb is that if you are dealing with a continuous random variables like height, weight, that type of continuous random variables, so the rule of thumb is that n got to be minimum 30. But usually, you will see that later. We will discuss that. You do not want to go with a very small, like a 20, 10, 20, something like that. So larger than, your answers are good. So this is the mathematical statement. Mathematically, you can prove this theorem under these two conditions. So if you have taken calculus, you probably know that limiting means that as n goes to infinity. Okay, so if you haven't taken calculus, that's okay, you don't need to bother with that. The limiting, as n goes to infinity, as n is, sample size is getting larger and large, the x bar minus the mean, so in other words, we are going to get rid of the mean and divided by the standard deviation. So we are converting this into the z curve. So this will follow a z curve. So that's the theorem. Okay, so which means that the larger than, this is always is going to be correct as long as this is correct. So we basically we can use this z table to figure out probability. So this is a very powerful theorem. So I will very important theorem. Okay, so even if this is not normal, we could use the table to figure out probabilities. So next I will do some examples with that.